Just so everyone is aware, this presentation will be recorded for future distribution. We will also have interpreters as well as live captioning. We do have captions available as well as interpreters. You can see the live transcript button in the bottom menu if you would like to use that. So I'd like to go ahead and get started with my introduction about this talk. First of all, welcome to our CREST presentation. CREST is a network for collaboration, research, and encouraging equity, specifically in areas of sign language related to technology. Please look to the chat box for more information about this network. Today, we are honored to welcome Dr. Sevgi Gurbuz from the University of Alabama. Dr. Gurbuz works in the Department of Electrical and Computer Engineering. Today, her presentation is entitled RF Sensing for ASL-based Human-Computer Interactions. I personally am looking forward to this presentation very much and learning more about this work with technology. Please feel free to use the chat box to discuss this presentation as we go, and to bring up any topics you may want to hear about. During the presentation, if you would like to pose a question, please use the Q&A option on your bottom menu. If you agree with a question or like it from someone else, you can also vote for that question to move it up. With that, I will turn the floor over to our exciting presentation for this afternoon. Thank you so much for joining us, and welcome.
Thank you very much for inviting me. I'm similarly very excited to be able to present to this group and to learn from you and hear your responses to our research and your new ideas. One
second, so we can get an interpreter.
Yes, ma'am.
Screen.
If you wouldn't mind going back, Dr. Gurbuz, and just starting over again, that would be perfect.
Yes.
Thank you so much.
So
okay,
would you like me to stop sharing or?
No, you can keep sharing, just
okay.
If you want to start your remarks over. Thank you.
Yes, ma'am. Yes, so thank you very much. I'm very honored to have the privilege to be able to talk to everyone today in the CREST network. I really look forward to hearing your ideas, comments, and reactions to our research. The title of my talk is RF Sensing for ASL-based Human-Computer Interactions. Before we get started on the core topic of this presentation, I would like to begin by introducing my research team, without whom none of this would have been possible. So as Dr. Quant mentioned, I am an electrical engineer. My area of expertise lies in radar signal processing and in machine learning. Other members of our team include Dr. Chris Crawford, who is a computer scientist at the University of Alabama, specializing in human-computer interactions. Dr. Evie Malaia, who is also a professor at the University of Alabama, specializing in neurolinguistics, cognitive neuroscience, and natural language processing. Dr. Darrin Griffin, who is in the Department of Communication Studies. He's also a child of deaf adults, and he's been very helpful in teaching us more about deaf culture and deaf-centric research, as well as Dr. Cafter Gurbuz, who is also a radar signal processing and machine learning professor at the Mississippi State University. As you'll see in our talk, we've really benefited over the years from having lots of input from the Alabama Institute from the Deaf and Blind, as well as our collaborators at Gallaudet. A couple of years ago, we had the privilege of meeting Dr. Caroline Kovec-Pezarasi, who has been an advisory board member on our current project and has given us a lot of great guidance over the years. And more recently, in 2022, we started working with Dr. Kenneth DeHaan at Gallaudet University, who we are now pursuing joint work actively regarding the topic of radar-based human-computer interaction. So what is our objective in this research? I'd like to emphasize that the main research question we're trying to address is how we can design technology to better interact with people who use American Sign Language as their primary mode of communication. I think it's important to emphasize the technology interaction aspect of this question, because so much of ASL recognition research is motivated by the different question of how we could develop technology to facilitate hearing and deaf communications, which I feel is a much larger, more daunting problem. In order to enable that kind of interaction, the research is mostly focused on how to do a complete translation of sign language. And that's a much more larger scale problem than I think how we can use ASL to control devices. I think our question is a little bit more of a doable problem in the near future. And so I'd like you to kind of take our results and maybe view our perspective on sensing from this perspective. So if we want to enable device control with sign language, the first question we must answer is, what would be the best sensors for doing this? There have been a lot of work on doing wearable sensing. I kind of purposefully picked out the most grotesque pictures of wearables in this image to just relay the fact that wearables present a tremendous burden on the user. It directly interferes with daily life. And from all that I've read, it's not really something that I think a lot of people in the deaf community want to use for interacting with technology. So we've kind of eliminated from our own perspective the idea of trying to incorporate wearables in our research. Instead, we've been focusing on non-contact devices. And in this realm, video is really the first and most important sensor that comes to mind. As many of you know, video has really enabled a lot of wonderful communications applications, not just for the deaf community, but for, I think, everyone globally. Being able to do video conferencing, being able to communicate with cell phone applications, these have really, really had a tremendous benefit, even like what we're doing today, where now I can communicate to you via video conferencing. But if we think about how we might try to interact with devices in the context of some of the newer ideas that have come out, such as smart environments or environments where the technology is trying to provide us a health service or some other kind of protective measure, you're talking about sensors which are embedded in our environment all the time, 24/7. And in this context, I think video raises a lot of concerns among the potential users, because now there's questions or concerns of video surveillance, technology being abused, a lack of privacy. And so when you think of this, we kind of steered away from video and wanted to look at alternative sensors that might be less invasive on a daily basis. Other limitations of video include that in the dark, when it's nighttime, you won't really get a good image of what a person is doing. The field of view of video cameras can be quite narrow, and that presents another limitation. Think of a scenario where maybe someone might be in their bed and they need something, they want to use technology, a personal assistant, maybe a robot in the future, to kind of call out to that device or robot and have them come assist them. Well, it'll be both dark and you most definitely won't be in the line of sight of that sensor. So we need to find something that can be used under these kinds of conditions as well. And in this context, I think radio frequency, or RF sensing for short, brings unique opportunities. It operates remotely. It doesn't have to be on your body. It can be embedded in the environment. It has a wide field of view, so you're not really restricted in terms of where you're located. There are antennas that have been designed which are that can perceive signals from 360 degrees, so you can potentially be located anywhere in the room. Because it's actively transmitting its own signal, it doesn't require sunlight. It can work, therefore, in day and night. And it's really not affected by what you're wearing, any type of jewelry you might have, the color of your skin, or anything like this, which may be a factor in video. So these are some of the benefits that we get from using RF sensing. Of course, every sensor has its limitations, and the main disadvantage of RF sensing is that it cannot perceive facial expressions. This is significant when we talk about sign language, because there are a lot of grammatical constructs that rely on facial expressions, and these type of small movements and expressions will not be captured by RF sensors. Another disadvantage currently is that finger spelling would be difficult to perceive with RF sensors, because finger spelling primarily relies on recognizing hand shape. And to recognize hand shape, we would really need a lot more resolution than the current devices out on the market are providing. Now, I put in parentheses that this is a current limitation, because for the purposes of automotive sensing and self-driving cars, there are companies that have now been trying to build RF sensors that can generate high resolution point clouds. And this is really just a technological limitation. When more and more commercial devices are constructed that have higher spatial resolution, I do believe eventually we'll get to the point where we would be able to recognize hand shape with radar. But currently, with the technology that we have in our lab, this is currently not possible. So what do RF sensors measure? What can we acquire? There are three basic measurements that we can make with RF sensors. The first is we can measure velocity. RF sensors do this by using a technique known as radio detection and ranging. This is often shortened with the acronym RADAR, or radar for short. This is the same way that police officers will point a radar gun at a moving vehicle to measure its speed. The benefit about the sensor that we're using, though, is that it doesn't measure just one overall speed. It gives you how fast every point on the body is moving. And when I show you what some of the RF sensing images look like later on in my talk, you'll see that this allows us to recognize unique patterns in the data, which we can use for the purposes of sign language recognition. Radar also measures the distance between the sensor and all the different points on the body, as well as the angle at which the person is relative to the sensor. So these are the three basic measurements that we get. As a result, there have been a lot of new and budding applications for RF sensors more broadly than human-computer interaction. And these includes health applications for aging in place, health for assisted living facilities to be able to have the capability of detecting when an elderly person might fall. It also includes doing data analysis. So if we want to predict, for example, whether or not someone has a persistent condition that might generate imbalance in the way a person is walking, we can try to use radar to analyze gait patterns. We can recognize activities. So we can recognize if someone is sitting down or standing up, running, using a cane, sitting in a wheelchair, things of this nature. We can also measure in a remote fashion vital signs such as heart rate, respiration. When someone's sleeping, we can measure the vital signs to try to assess sleep state. And as I mentioned, there is this burgeoning field of self-driving cars and automotive radar. And so there's a lot of new applications coming out for pedestrian collision avoidance, also in-cabin monitoring, things like occupancy sensing. You may have heard in the news events where somebody forgets a child in the vehicle, and unfortunately that child, after several hours pass in a hot vehicle, the child dies. To prevent things like this, occupancy sensing and vital sign sensing in the vehicle are also burgeoning applications for passenger monitoring. So what we're proposing with sign language recognition represents a new application of RF sensing that has built on existing work that started in 2015, most famously known by the Google SOLI project, SOLI, where Google proposed using radar as a method for gesture recognition. And they've currently integrated radar sensors in their Google Pixel 4 camera for non-contact device control. And in this case, they're looking at things like swiping motions, using virtual knobs, and things of that nature. So obviously, sign language recognition is a much more complex problem than trying to recognize a handful of hand gestures. And we are interested in pursuing this problem both from the perspective of using RF sensors only, as well as in cases where the user initiates this mode of device control, we could look at how we could use RF sensors together with video, where video would be providing the information on the facial expressions and hand shapes that RF sensors are limited by and cannot acquire on their own. So this has been an evolving progress. Just to let you know kind of how our research team was first formed and how we've progressed over the years, I put together this timeline for our project. The idea of using RF sensors for sign language recognition was really started by us in 2017 when Dr. Crawford, myself, and Ali Gurbuz at Mississippi State first got together, and we thought that this would be an interesting research idea. Shortly after we first discussed this idea, Dr. Crawford reached out to Dr. Griffin as a professor in communication studies and someone who we knew in our community who is active in deaf community research and deaf advocacy to see what he thought. And that first meeting was really instrumental, I think, in forming the philosophy for our group, because Darrin very nicely kind of informed us that if we were going to build something for the deaf community, that obviously we needed to get the deaf community involved in it right from the get-go. And we needed to have a deaf-centric design approach rather than kind of going off on our own as engineers and building something that therefore might have a limited value. So we started actually by not collecting data, but by first doing some focus groups with the Alabama Institute for the Deaf and Blind and recruiting people from the deaf community in Tuscaloosa to see what they thought about the idea in general. Like, if we could build something like this and get it working, would this be something that you would be interested in using? Do you think there is benefit and value to this idea of using RF sensors for ASL recognition? And we got a lot of positive feedback from those initial focus groups, which then motivated us to recruit some participants from our local community who would just articulate single signs of ASL and see if we could classify and recognize any of those signs. So we did our first data collect in May 2018, and that really provided us the initial results that we needed to finally get funded and submit our first proposal in June 2019, which was funded, and the project actually started in October of 2019, which also coincides with the time around which we submitted our first results to technical publications. Those publications first came out in 2020, but as you remember, this is also around the time when COVID first hit. And so we found ourselves
in the position where we were just starting to be able to get going, but now we couldn't see or interact with anyone. And in order to do sign language research, you really need to have data from people who are fluent in ASL. And around that time, when we started doing more and more research into what was currently accomplished in sign language research, we came across a slew of papers, especially those involving the Kinect sensor, I might say. I think members of the computer science community working in video have a lot more data from fluent signers, but we noticed that researchers using the Kinect sensor did a lot of publications where they were just acquiring data on themselves. This was also around the time where myself and some of the members of the team had started to enroll in ASL 1A, because we figured if we were going to do sign language research, we needed to learn something about sign language. And it was painfully obvious to us that clearly the way that I, as a learner, tried to articulate signs is completely different from the way Darrin articulates signs with the coda, and completely different from the way an interpreter or a fluent person in the deaf community
would be articulating sign language. And given that we couldn't really go out and collect data from deaf participants, we started to study what we call imitation signing. And I will talk about imitation signing and its differences from fluent signing later on in the talk. But this period of COVID between like 2020 and 2022 primarily involved working on imitation signing, studying how we might be able to build algorithms based on simulated data and things of that nature. And we'll talk about that more later on in the talk. The next major milestone for our project, though, was just this past April, where we finally had the opportunity to visit Gallaudet University for the first time on an extended basis. We spent a week working with Dr. Dahan, and we collected data from, I believe, 17 participants on campus. And we're currently working on processing that data with the algorithms that we developed during COVID to try to get results that will be meaningful and form the basis for our future work. So this is where we kind of are right now. I want to show you this image of the way our test setup was done in our lab. So this is a picture of my lab at the University of Alabama. And you'll notice that we have a participant who, in this image, is sitting about 1 meter away from the sensor. The sensor is small. It's about the size of your cell phone, but the actual size of the chip that's on the board is just about the size of your fingernail. So it's actually quite small. And the way that we conducted the experiments was to use a computer monitor to present in English a word that we then requested the participant to articulate in sign language. Before the participant does the experiments, we do go over with them what this sign would look like in sign language to kind of avoid any ambiguity about the articulation itself. Even though the person is sitting here 1 meter from the sensor, in general, you could be several meters away from the sensor and off to the side, and you would still be able to pick up the sign. But for this very initial data collect, we wanted to be closer and avoid trying to consider all of the possible use cases because we were doing our first testing on sign language. So that's how this was configured. But in the data collect that we did this April at Gallaudet, we collected data at different distances and at different positions and angles within the room so that we will be able to report results under much more realistic conditions, more daily conditions in our future publications. So I'd like to kind of show you what the data looks like. The data that we get from an RF sensor is actually just a stream of numbers. And we apply signal processing techniques to convert them into various kinds of images that can reveal to us what some of the physical measurements are. So the first type of image we can generate is something that's known as a micro Doppler signature. And really what it is it's a plot of the velocity coming back from every point on the human body as a function of time. So the horizontal axis is time and the vertical axis is velocity. but it is
Hi there,
directly.
Real
Dr.
quick.
Dr.
Yes.
Gurbuz. Hi,
Mhm.
I'm so sorry to interrupt you
No,
right
that's
now.
okay.
I just wanted to give you some information. Your audio, the sound is a little bit choppy.
Off? Okay. If
Yeah,
I
it's
raise
a
it
little
like
bit,
this, is it better? Can you hear me a little bit better when I raise it like this?
potentially. It's your audio's been, the signal has been coming in and out. Sometimes it's very faint. Right now it's very strong
Okay.
and clear.
Okay.
But if there's anything you needed to change, I just wanted to make you aware of that. And
Yes.
right now it sounds perfect though.
Okay,
Of
I
course,
think
of
my
course.
desk was probably interfering with the microphone of my laptop. So what I will do is I will put some books under my laptop so that
Okay.
the microphone is closer to my mouth and raised from the table, so there's hopefully less interference. Is this better?
Perfect.
Okay, thank you for letting
Yes.
me know. I appreciate it.
Sure, no problem. Thank you. So if you could just go back to the beginning of this slide and start
Yes,
your
ma'am.
explanation from the top of the slide, that would be great. Thanks.
Okay,
Yeah, this looks
for
really
sure.
interesting.
Yes. So the original form of the RF sensing data we get is just a time stream of numbers. And we apply radar signal processing techniques to convert that stream of numbers into images. And there's a number of different types of images we can compute that reveal the physical variables that I talked to you about before, basically distance, angle, and velocity. So the image I'm showing on this screen is what's known as a microdoppler signature. And it shows you how the velocity varies with time. This includes the reflections from all the different points on the body. So it's not just the hands or the arms, but every single point that the signal reflects off of. Because it's also reflecting off of stationary objects, at 0 speed, you get a strong red horizontal line. This is the reflections from all the walls, furnitures, any kind of non-moving object that you have in the room. And the squiggles that you see, which are up and downward, are the actual movements from the hands and the arms when the participant is articulating a sign. If the peak is upward, it means that the person's hand or arm is moving towards the radar. If it's downwards, it means that it's moving away from the radar. This is a sentence which has 2 instances of the sign U. U, for example, is a very easily identifiable sign because it involves a strong movement towards the radar initially and then backwards. And so you'll see a peak that goes up, followed by a peak that goes down, for example. But aside from, of course, some of these specific signs, you can see that unlike video, this is not the type of data where someone would be able to look at it and immediately know what the person is saying. It also means, though, that I can't tell what's going on in the room. I have no idea where this person is located, what the orientation of the furniture is, what is written on the walls. And this is kind of the privacy protecting aspect of this data. Yes, it's more difficult to interpret, but that also protects the user. Other ways that we can visualize the data include plotting the distance versus velocity. And on this slide, I've tried to show you different snapshots of the data at different times. So we have a sequence of 5 different images collected sequentially. And the leftmost image shows what you would see if the person is just sitting at rest with the hands on the knees. As the person raises their hands from the body and moves to articulate the sign, in the next frame, you'll see that there are some additional blips in the data showing that there's been a change in position and change in the speed. This becomes more pronounced in the third image, where now the hands are really quickly moving towards the radar. And as the person then retracts their hands back towards their body, you'll see that eventually the images converge to the way it was in the beginning when the person is again at rest. So this is an example of how the distance and the speed varies during the course of articulating the sign breathe. Another way that we can visualize the data is by plotting the distance versus angle. The angle that I'm talking about here is the angle horizontally. So it would be indicative of the hand moving off to the side, left or right. Now, there are many signs which might be directional towards the person you're speaking to, in which case you wouldn't really see much of a change in angle. There are also newer radar systems that have been built, which include both a horizontal antenna as well as a vertical antenna. And for those newer systems, you could actually generate another sequence of images, which now tells how much the person's hand is moving up and down. Overall, though, the main takeaway from these images that I'd like you to get is just the idea that these are not very easily interpretable by people themselves. If someone were to intercept the data and look at it, they wouldn't be able to pick up who you were. They wouldn't be able to see where you are or know anything about your personalized environment in space. Conversely, though, the problem is that humans can't really look at this and recognize sign language ourselves. We need to be able to program the computer to somehow be able to do this for us. And so I'm going to talk in a little bit moment about how the computer does that. There are some things that we can visually interpret from the data, and I have a few slides to show you that. The first has to do with whether or not you're articulating sign language using one hand versus two hands. And there's kind of two cases of this, because in some signs, both the left and the right hand are doing the similar thing, like in the sign for breathe, both hands are moving forward and backward at the same time. And in those cases, we can see that similar to the case when you have only one hand, you have distinct peaks at specific moments of time. So in the case of the sign for you, you have a distinct upward peak followed by a distinct downward peak. You can see that the dominant directions are sequential. The same with breathe. You have a dominant upward, then a dominant downward, followed by, you see there's a slight downward and then a slight upward, and those are the movements for the person moving their hands back down to the knees. So this is one characteristic of the data that I would like you to contrast with what happens when you have hands that are moving independently of each other. Now you can see that there are upward and downward peaks at the same time. And so what we've seen is that by looking at these type of symmetry properties, we can identify in the data whether or not the sign involves one hand or two hands. And sometimes this can be used to improve your ability to recognize different signs. Other things that we can notice, for example, is whether or not the hand is faced palm outwards versus just seeing like the edge of your hand, because when your palm is facing outwards, you get a stronger signal back, which results in more redness in the image. And we can also count, for example, the number of repetitions someone can do during the course of a sign. So, for example, a sign like knife, where you're repeating something a certain number of times, we can count the number of times that movement has been repeated. But again, aside from some of these really distinct characteristics, we have to rely on a computer to figure it out. So how does a computer do this? This is just kind of a conceptual sketch that I've tried to do. Doesn't really involve radar. This idea would apply to any kind of image. So it's a concept that's really used in computer vision. It's much more broader than radar. But how would the machine learn how to recognize things in general? So I want to take this kind of fun case of, if we wanted to recognize our mascot, whether it was the Gallaudet bison versus the Alabama elephant, how would we go about doing that? So if we think about it, what makes these two animals different? Well, their color is different. One is brown, the other is gray. One has horns, the other has cute flappy ears. One has hooves, the other one has really big clumpy feet. And the Gallaudet bison is wearing a white t-shirt in this image, whereas in Alabama, we usually like to dress up in red because crimson is our school color. So how does a computer take that information? Well, you'll first extract and compute the color You'll try to identify the number of horns, the number of feet, the color of the shirt, and that forms a point in the computer's memory, what is usually called a feature space. It's just a mathematical way of representing computed values from the data. And so if I wanted to try to teach a computer how to recognize a bison versus an elephant, I would get a whole bunch of different pictures of the bison, and I would calculate what the color value of that picture is, how many horns are present in that image, how many hooves are present, the color of the shirt. And each one of those images would show up in the computer as a point, which I've labeled as the blue points here under the category of bison. And I would do the same thing for the elephant. And so for every image of the elephant that I presented the computer, it would calculate these values, and it would, for each image, it would generate a new point. And based on looking at those points in space, I would try to determine mathematically a boundary. That's represented by the dark black line on the slide. And so it'll compute this boundary based on the images that we use to teach it. And when it gets a new image that it doesn't know whether it's a bison or an elephant, it'll compute these values, plot it in this space, and basically say, which side of the boundary am I on? Am I on the blue side or am I on the red side? And if I'm on the blue side, then I'm going to declare that I've recognized this image as a bison. And if I'm on the red side, I'm going to declare that I've recognized this image as an elephant. And it'll do the similar thing with the radar images that we provided, but using various mathematical techniques. Of course, the parameters that the algorithm is computing might not be easily interpretable, like the example I've given you here. So I'm not going to really show you what those numbers necessarily look like. But the main kind of concept I want you to get away from this is the idea that to be able to recognize sign language using video or radar or any other sensor, we need to provide the algorithm a lot of data, and it will use mathematical techniques for computing the best values that will allow it to differentiate between one sign versus another. And it'll compute where the best place it can draw the decision boundaries are. And accordingly, when we provide it new data, it'll tell us whether it thinks the image is one sign versus another. So in the rest of my talk, I want to talk about what some of the results we've obtained by using this type of algorithm. This is known more broadly in computer vision as deep learning. And in particular, I want to talk about the data that we provide the deep learning algorithm, because your algorithm or your results are only as good as the data you provide it. You have to teach the computer. If you don't provide it good inputs, it won't be able to provide you accurate outputs. And in this context, fluency is very important. We've worked on how we can generate our own synthetic data to help teach the computer so that we minimize the amount of actual human data we have to provide the system. We'll talk about what some of our single word recognition results are currently, and I will describe to you, and we can discuss the work that we've done on triggering and controlling devices and some of our future research directions. Before we kind of get into the details of the methods and our results, I wanted to kind of give a little pause, both for the sake of our interpreters as well as our listeners. And if you have questions that have accumulated, I've noticed that there's a lot of things coming up in chat. Before we go on to some of the numerical results, I'd like to give the opportunity to our listeners to maybe ask some questions, and then we can kind of continue with the last 10, 15 slides that I have.
All right, just want to make sure that I am on spotlights. Dr. Gurbuz, do you mind moving your video? If you can tilt just your camera down a little bit so we can see your beautiful face. Thank you.
Thank you.
So I do see one question in the Q&A from an audience member asking, Are you using Connect?
So the results that I'm going to present today do not use Connect. However, we have been working on methods whereby we could use Connect to simulate radar data, and that will help us in teaching the computer better models. So I do think Connect is helping for teaching the computer how to recognize sign language. But to be honest, if I'm thinking about developing a device that has multiple sensors for sign language recognition, I'm more interested in fusing radar with video, because the radar already provides the depth information that you get from Connect. So I feel like if we built a system that was video plus Connect plus radar, that there would be redundancy based on the information that we're getting from each sensor. That having been said, when we consider the data collects that we do in the future, we are planning to build the system so it incorporates, video, Connect, as well as radar. And actually, this past April, we wanted to collect data with LiDAR as well. The system crashed, so we couldn't. But in general, given that it requires so much time and effort for our participants to come in and spend time to give us data, we want to collect the data with as many sensors as we can, so we can make comparisons and we can validate this intuition that I have about radar versus Connect. That will inform us on, when we go to the actual prototyping phase, which sensors we actually need.
Sure. So I think I understand you're trying to collect more than just one data type.
Yes.
In terms of training the computer, and hopefully more in the future, you can use what you've trained the computer to identify new models. Okay,
Right.
That makes sense.
So one thing we could do is we could train with video, Connect, radar, and LiDAR, but then only test using, let's say, radar and video. Because that would mean that the user would only need to have on their device a radar and video. So I think we need to be creative in terms of how we mix and match and use sensors.
Cool. I see another question in the Q&A. I'm not sure if you want to open the Q&A yourself and just read it, or.
Let me try to do that now. I haven't been able to, I don't know if I'm in share mode that I'm not able to see
Okay,
the Q&A.
No problem. The gist of it is, how many hours of sign language training data will this technology need before it could approach a similar level of performance as today's consumer level voice recognition interface?
That's a great question. So commercial voice recognition software, when it's initially deployed, uses millions of data samples for training. Currently, the amount of data we've collected is more on the order of, I think, 2,000. And we've been trying to synthesize data on the order of tens of thousands to be able to train the models we have. One idea that I have kind of philosophically, stemming from the way that voice recognition developed, is that, every time we use a personal assistant that's voice recognized, that data gets sent back to Amazon, Google, Facebook, etc. And they're continually updating their models. So if they started out with millions, I'm sure right now they're on tens or even 100 of millions of samples. This really segues into how we're trying to develop our current data collection technology, because it takes up so much time and effort from our participants in the deaf community and to give us data. And when they come to the lab, they're not really doing something that's very fun. I'll be point blank. And I want to develop a process that's sustainable, which can give us a lot of data over time, So we're continually improving our models. And so in order to do that, we need something that's fun, that can be interactive, and that can have a benefit for the participant, and which also observes sign language in as much as possible its original form. If you think about the experiment as I've described it in my earlier slide, the person sitting down with their hands on their knees, they come up and they do the sign and then they put it back down. Well, that's not really very natural, is it? And so our first task that we want to actually accomplish together with Dr. DeHaan, and our goal is to maybe roll out like a first prototype, if possible, in the spring of 2023, is to connect all of the pieces of our system together so that it can interact with a participant. So rather than having me describe to the participant what they should say, it's just going to be a software program which is standalone. Hopefully, I want to design it in a way that involves minimum explanation on my behalf. Ideally, this would be something that I just take the sensor, connect it to their laptop, they open up the software, and then they start interacting with it. And all the interactions would be recorded. Yes, there's going to be a huge annotation work. There's going to be a huge amount of work to try to generate ground truth from this data. But the data that we get will be real data. It'll be actual ASL. It won't be contrived. And if we can continue evolving our algorithms using this system, then over time, we'll have more and more data, the algorithms will become better, and the results will be more relevant. And so I don't really think of this in terms of number of samples, but I view it as a shift in paradigm, because to my knowledge, even in the video community, they have databases of sign language. That's still not continuous discourse. So I feel like rather than trying to just get more and more data and repeat the same methodology that has been done before, that we just need to shift. We just need to change and try to approach the technology development really the way they've done it in speech processing. I think speech processing is a much better role model for this than what we've been doing so far. So we're evolving.
Understood, and that makes sense. I really love your vision of how to make this more natural, more entertaining, or as close to fun as you can get for participants. Something that's going to be rich data, not, like you said, simplistic or contrived data of individual signs. So I really love learning about that. I think at this point we're good on questions, and I will turn the floor back over to you to go through the rest of your slides.
Okay.
I know there's been a lot of talk in the chats and back and forth about comments, but we'll hold on that for now. So, and I will ask anyone to put specific questions in the Q&A, please, moving forward.
Yes, thank you very much.
Thank you so much.
Okay, so earlier in my talk, I alluded to this issue of imitation data versus fluent sign data, and I want to kind of describe this a little bit more. So what I've seen in some groups is that they've had a hearing person who tries to articulate the sign after watching videos. Some groups are a little bit more conscientious and give several hours of training to their participants before doing this. However, if you go into literature on linguistics relating to sign language, you will find that there are publications which say that it can take a hearing person at least 3 years before their signing can be perceived as fluent by other fluent signers. So just showing a few videos or even several hours of videos to a hearing person is not sufficient to enable them to articulate sign language the way an actual fluent signer would do so. And if you look at the data visually, you can see that there are a lot of errors. Some examples include, hesitation and then doing rapid movements, or doing the number of repetitions in a sign an incorrect number of times. So if someone is trying to articulate knife, instead of doing it once or twice, they'll just go and do it like 5 or 6 times. And so this becomes really damaging because you're teaching, if you use this data, you're teaching the computer the wrong thing. Now, what some papers will do is, because all of their data is from imitation signers, they will use the imitation signing data both to teach the computer and to test the computer. Some authors have justified this by using the argument that in developing technology for human-computer interaction, we want it to be able to be used by everybody. And I'm actually, when we get to the end of the talk, I'll be very interested to see what your thoughts on this are, because I'm a hearing person, obviously. From my perspective, I feel like, well, if I'm designing something that uses ASL, it needs to be for that community. So it needs to be for a fluent signer. Why should I care about how an imitation signer signs? But I've also had those who have said to me, and I feel there's some logic to this, that if someone is learning ASL and there's a spread of knowledge, to my understanding, in the deaf community, where there are a lot of also sign language learners, that you would also want to develop a system that is open to the learners. So I do think it's an open question, and it's a design question, as much as maybe a cultural question of, when we provide data to the computer, do we want to provide fluent only data, or do we want to broaden it to different levels of learning? Do we want to have the computer understand different levels of learning? Should the learning level be provided as an input to the computer, and maybe then accordingly the computer picks different models? These are all kind of open questions that we have to think about. But I think the one question that is clear, should you take a hearing person and teach a computer using what a hearing person does, test a computer using what a hearing person does, that feels to me to be quite wrong. And during COVID, we tried to do some studies to show this. I want to kind of break down first the pictures that are in this image. You might remember the slide that I had earlier, where I showed you the bison and the elephant, and I tried to show you how different characteristics mapped to different points, and how the computer tried to decide a decision boundary. This image is basically taking a lot of different mathematically computed characteristics, flattening them into 2 dimensions. So you have component 1 and component 2, and showing you where those points are for different signs. This data involved 20 different ASL signs. So there are 20 different colors in each one of these images. In the left image, I'm showing you the points corresponding to each sign for an imitation signer. And in the right image, I'm showing you what it looks like for a fluent ASL user. If you look at the left image for the imitation signers, you'll see that the colors clump. The colors clumping is a good thing for recognition, because it means that it's easier to draw a boundary between the different groupings. So it will be much easier to classify the imitation signing data. You will get much higher results because it's easier to draw the decision boundaries. The signs are more similar to each other. And I hypothesize, I'm not a psychologist, I'm not a neuroscientist, but we hypothesize that, just thinking about how I am trying to learn ASL, I'm memorizing it. I don't really know it. I'm memorizing it. So I try to do the same thing each time, which means that I'm more easily predictable than what an actual natural language speaker would do. And this interpretation, I think, is verified by the figure on the right, where you can see that all of the points are so wonderfully intermixed together that who knows how you would design a decision boundary between this, right? The complexity of the problem, I feel, is revealed in these images. And I feel that even without going further, these 2 images really speak strongly to why you should not use imitation signing data in developing and benchmarking machine learning algorithms for ASL recognition. You could actually design an algorithm that takes the data and just tries to decide whether or not the data belongs to an imitation signer versus a fluent signer. So this is a binary classifier. And if you do this, we did this several years ago, so it's not the best algorithm you could use for doing this, but even with looking at just 2 characteristics of the data, you get 76% accuracy in being able to know whether the data you got was from someone who is imitating versus someone who's actually fluent in the language. How does this impact the training of our models? Well, let's look at 3 different cases. Case 1, the case where I teach the computer using imitation data and I test the computer using imitation data. With 20 ASL signs, you get 96% accuracy. That means almost always the computer can correctly identify the sign that was been articulated. Let's compare that to case 3. Case 3 is the case where you're teaching the computer with fluent ASL data and you're testing it with fluent ASL data. The same model now drops to 78%. Okay, so if you're thinking about validation of algorithms, using imitation data is overestimating your performance by 20% or a little under 20%. So any paper which publishes data where they've tested it on themselves, they're completely over optimistic in terms of how well they're able to do. Case 2 is something that we looked at because we were like, well, we can't, it's COVID, we can't collect data from fluent signers. Is there any value at all in collecting data from hearing signers or hearing imitation attempts? Does that inform the computer at all on anything valuable for recognition? And so if you look at case 2, which is where you teach a computer on imitation data and test with fluent data, the imitation data from a hearing person is so terrible in terms of its accuracy of articulation that you only get 24% accuracy. I mean, flip a coin, you would do better than that. There, in my opinion, therefore, is no value in using imitation in this way. Now, there are algorithms that have been developed in computer vision, which are known as domain adaptation algorithms. And what these algorithms trying to do is it tries to make one data set resemble another data set. So one thing that we've also looked at, and I didn't really put the results on here because I didn't want to focus on it, but we've tried to take imitation data and using computer vision, make it look more like fluent data, and then teach a computer with that. If you do this, you do much better than 24%, but you still don't do as good as just trying to synthesize the data from scratch, which is what I want to actually focus on in my next slide. So instead of relying on imitation signers, the idea is, can we come up with a way to generate simulated data? And the idea would be that we take a small amount of real measured fluent ASL data and put it into this algorithm. It's called a generative adversarial network in computer vision. And we've developed kind of our own versions of these models that are specific to RF ASL data, which takes into account things like handedness and the number of strokes, making sure that the average hand speeds are consistent and things of that nature, to generate this time a large amount of simulated synthetic ASL data. The idea being that, I don't want to take a participant and put them in the lab for hours and hours. Let's just get a few data samples and try to grow the data synthetically. This method has been very effective in improving our performance for ASL recognition. This chart here shows you the recognition accuracy for 100 ASL signs. And if I used only the real data that I was able to acquire. Now, in terms of sample size, the number of sample points per class is very low. It's much lower than what you would use in computer vision or natural language processing, just because it requires so much time and effort to be able to collect this data. So we have 20 samples per class in the leftmost bar, which shows 49%. And it's labeled with top 1 accuracy. What that means is that I'm going to give you one option for what the sign is and whether or not that selection or decision actually matches what the person did. 49% accuracy. If I add in the synthetic data that I've generated, and usually we're generating now tens of thousands of synthetic samples, so you have a much larger amount of data that you're providing, albeit it's not as good as having measured data, but we're trying to close the gap. Your accuracy now goes up tremendously by almost 30%. You're going, or 20%, 28%. You're going from 50% to 78%. What I've labeled in the rightmost block as top 2 accuracy is, if I told you, instead of saying what the person has done is sign X, instead of saying that, if I say, well, maybe it's this sign or that sign. So it's the percent of times where of the 2 possibilities I tell you, one of them is correct. Then we're able to do that 94% of the time, which is actually pretty good. We've wanted to compare these results with what you would get in video. So what we did was we went into some of the ASL video databases that have fluent signing data. And we've extracted from those databases the same 100 signs that we acquired the RF data from. Now, albeit these are data that have been collected in a different environment with different people. So I don't view it as an absolute comparison. To really make an absolute comparison, you'd want to have both of the sensors collecting data from the same person at the same time. Nevertheless, it gives you an idea of a ballpark idea of how good you are. And what we found was that for the option of you exactly knew the correct sign, RF data is about 18% better than video. And by video, I mean RGB only. This is not using Connect. This is just video. Top 5 means I'm going to give you 5 possibilities, and one of the possibilities is actually the correct sign. For that option, they perform comparable. Yes, there's a 3% difference, but as I said, I'm collecting this from a different database. There's different numbers of samples and so forth. You know, you have to take the numbers with a little bit of grain of salt. Okay, so the upshot of this slide is just to show you that if you're looking at video only recognition, RF does just about the same or maybe slightly better. And what's interesting about this, though, is that these 2 sensors are actually measuring different properties of sign language. If you think about what RF sensors are giving you, we're using only the microdoppler signature in generating these results right now. So that means I'm giving you patterns of what the velocity from each point on the body is doing as a function of time. That's it. What is video doing? Video has expressions, it has spatial information. It's providing you a different, completely different aspect of this language. This is what I think really makes the idea of researching the fusion of video and radar interesting, because now you can get, if you were to fuse them, you know, one sensor is compensating for the weakness of the other. You know, video, because of the limitations in frame rate, are not able to get as frequent a temporal sample as radar can give you. It also doesn't really have very good depth estimation. That's why people have looked into Connect for augmenting video, because Connect gives you a depth measurement. Well, now radar can give you that depth measurement. It can give you patterns of velocity. It can give you angle in both azimuth and elevation. And you can use the video for getting both azimuth, elevation, as well as hand shape and expressions. So I feel like these 2 sensors combined give you a much more complete picture of what is going on with ASL than using any one of them alone. That having been said, you know, when you're doing video conferencing, obviously video gives you a very good capability of commuting. But if you're looking at some of these private situations where you want to have like an Alexa next to your bed at night and you're in your pajamas, you don't want to turn on a video camera. Well, what these results are telling you is that RF can do pretty good for a limited number of signs. And that's really where I think there's the opportunity when you think about this, not just from the perspective of how radar might be able to be used as a tool for understanding language, but more for, you know, just the broader applications of human-computer interaction and maybe how an ASL user might want to be able to use and take advantage of new concepts for technology that's getting more and more integrated in our personal living space. Other things that we've looked at is this issue of triggering and controlling devices. And one of the big problems in doing this is, the radar will pick up any movement. So if you're just like walking around your home and then you go wash the dishes, pick up a book, sit down and get up, these daily activities, the radar is picking up this as well. But we want to be able to make sure that we can identify and differentiate between that versus the movements that are involved in articulating sign language. So how can we differentiate ASL from daily activity? If we're given a continuous stream of data, can I detect, segment, and classify the signs in that data stream? So we have done some initial experiments about this, where we've had a person like walk around, sit down, then turn towards the sensor, articulate 1 or 2 words. Now, this isn't continuous discourse. It's just 1 or 2 or 3 words. But in this context, we found that we've been able to separate signing from daily activity, and we have been able to segment the data to give at least 90% recognition accuracy, both of activities and the signs. So we're able to determine over which period of time what the person is doing. We are able to identify that they walked, then they sat, then they said month, then they said cook, then they said again, then they stood up again, etc. Over short intervals of time. So you can see this is only a 25-second snapshot. In the data that we collected at Gallaudet University in April, we've expanded this to include the person signing and moving throughout the whole room at various different positions and angles. So when we're done processing that data, we'll get much more updated results about how effectively we can do this in more realistic conditions. There is an ongoing question that, again, I think requires collaboration with the deaf community and deaf researchers. This entire project, we really benefit from collaboration with Gallaudet and AIDB. But this one is especially is a topic where I think I'm really not the person most well suited to pursue this, but I need to support deaf researchers in pursuing it. And that's the issue of how should you best trigger a device? And there's multiple considerations to that. We have only looked at what I consider to be the technical considerations. In other words, what type of movements are more effective for triggering a device? Does handedness affect this? How does the number of strokes involved in the articulation of the sign affect this? Does the location of the sign affect this? What type of movements are involved? We did a very, very small pilot study where we looked at these 15 words and tried to see whether we could use them for device triggering. And we found that we could do that, and that the best sign to use from this group was things like teach. Things that involve more kinetic movement, that are more unique, and especially are directed towards the radar, tend to be more easily identified than other types of signs. So these are technical considerations. But when you think about how to design a trigger sign, there are a lot of other considerations. And these are just cultural considerations, preferential considerations. People who naturally use the language should be the ones who determine how they trigger their device. So this is something that I would really like to find partners with to work on. And it's something that we are going to be working on with Dr. DeHaan. But again, more broadly, if people are interested in this issue, there's a lot of room for doing this. And I think one idea that Darrin had shared with me several years ago, which I'll just mention here, but maybe he can talk about in the Q&A, is the idea of, would you even want to design a unique sign for the purposes of device triggering? Again, that's an open question that I'm not really the person to answer, but I can definitely run the tests and analyze the data for it, if you will. So to kind of summarize where we are and what directions we want to go with, we're kind of in a year where we've just emerged out of the COVID lockdowns. This was the first year where we could really go to Gallaudet University and collect some data. During the Q&A before, I talked a little about the interactive gaming idea. And again, this is the idea of trying to make the experience meaningful while also acquiring natural discourse to the extent possible. And there's a number of contexts in which this can be framed. I think it could be framed just in terms of entertainment, like if someone's playing a video game. You can have embodiment games that involve a mixture of body movements as well as communication between the video game and the user. Other ideas include doing something that's educational for any group. I mean, we've had interactions with AIDB, so we're kind of brainstorming ways that maybe educational software for teaching STEM education to the K-12 grouping might be done. And that's kind of like a work in progress, which we're evolving on. And we need to pair up with people who are experts in deaf education to do that. We don't yet really have a partner in that area. We're looking and trying to reach out to people who may be interested in partnering up with us on something like this. But for now, what we've done has mainly consisted of trying to organize half-day workshops for NTID summer camps, and trying to provide the sensors to the students with a more user-friendly interface so that they can just play around with the sensors and see how they work and try to use that to teach them about physics and machine learning. So this is something that's still, again, we're just at the beginning of trying to develop the ideas for this gaming. And this semester, our goal is to try to actually put together all the different modules required to be able to design software that's interactive on any level. So it will be very, very rudimentary what we're able to accomplish this semester, but it's something that starting in the spring, we'll be able to build off of to make into a more meaningful experience. I feel like once we have this type of a system, it's something that we could just, for example, provide our collaborators at Gallaudet and other institutions like AIDB, and students could come and go. And ideally, our vision is they would use it whenever they wanted, however much they wanted. The data would kind of be continually dropped down to the cloud, where we could continually, annotate it, process it, to try to continue to build up our databases, and hopefully develop research projects that involve the study of sign language as a language, and also, the HCI aspects of it, and try to improve the sign language recognition technologies. We would like to try to develop an ASL triggered kind of prototype. This could be something that involves drones. I only bring up drones because it's something that's used in robotics teams. You can imagine, I don't know if any of you has watched Endar's game, there's a scene where the kid kind of uses hand gestures and movements to control spaceships. It might be fun for kids to see that they can use ASL signs and those types of gestures to control and operate drones, just as like a programming STEM project. There might be other ideas that you have, which we'd be glad to try to pursue, and also to pursue research in sensor fusion. And this is, I've been mostly focused on RF and video, but this includes RF and LiDAR, maybe RF and anything else that you can dream of, right? As we discussed in the Q&A earlier, we're very open to any kind of ideas for how different sensing modalities can be used to improve the experience of ASL users with technology. So my final slide really is just a picture of what we did at the STEM camps. And I'd kind of like to turn this over to Q&A. And if Dr. Griffin would like, as part of Q&A, to also talk more about kind of our community engagement, I think he would be the better person to talk about that, because I'm just an engineer, and he's really our guiding light in the project on these topics. And other than that, yes, I'm very grateful that you afford me the platform to be able to talk. And I look forward to hearing your thoughts and ideas and answering your questions.
Thank you so much for your presentation today. There was a lot of information, especially for me. And I believe so for our audience as well. I learned a lot. And I think there's a lot of new ideas that came from this. It was just a beautiful slide deck as well. Wonderful presentation. Thank you so much.
Thank you.
Unfortunately, our interpreters do have to leave at 1:15. Yeah,
Oh, yes.
right about now. So our interpreters have to go. They had a hard stop time, so we don't have time for our Q&A. However, we've seen our chat and there's a lot of ideas in there that have come up, a lot of thoughts that came up during your presentation that we will be saving in the transcript.
Okay.
We are also saving this recording and we will edit it to make it nice so the captions are there and the interpreters are clear with the video. And that'll be posted.
Thank you.
I am very much looking forward to following up with you. And please, to our audience, go to our website. It's in the chat box. You can see it there. And you can continue your involvement with this network and continue our chat with members within the network. So there's a lot of potential for collaboration.
Thank you.
I want to thank you again so much. I want to thank Stephanie and Michael and our team today. And I want to thank our captioner as well. So thank you again so much for accepting our invitation to come and present today. We appreciate it.
Thank you very much. It's been an honor, and I welcome any emails if anyone would like to directly reach out to us. I have my email address on the slide. I also have links to all my publications, or all our publications, on this website, and there's actually a special web page for ASL. So I would like to invite people to go check that out. And again, just get in touch with me with any ideas you may have or questions.
We will. Thank you.
Thank you.
Thank you. And everyone have a great rest of your day.
You too.